This is question 9 from the 2013 paper. Here we are up here. Part A. What is meant by chemical equilibrium? Chemical equilibrium is when the rate of the forward reaction is in balance or equal to the rate of the reverse reaction. Okay, so it mightn't be in perfect balance. It might favor the forward reaction or the backward reaction, but in whatever way it's going, the rate of the forward reaction will equal the rate of the backward reaction. So it's got some kind of balance. And why is a chemical equilibrium described as dynamic? Dynamic, the key word here is continuous. So the forward reaction keeps on occurring, it's continuous, and the reverse reaction keeps on occurring. Okay, so that's dynamic. The reaction, both reactions going in either direction are continuous. The reaction doesn't go to completion. And state Le Chatelier's principle. So Le Chatelier states that when a stress is applied to a system at equilibrium, the system at equilibrium will adjust in an attempt to relieve that stress. And part B, here's my pen. There. Part B, so it sets up this reaction here. We've got iron 3 chloride and a color solution of potassium thiocyanate. So it gives us the colors there, yellow on the left and red on the right. Mixed in a test tube, a red color appeared and the following equilibrium was established. Explain part 1 here. Explain the effect on iron 3 plus ion concentration on adding potassium thiocyanate. Okay, so the addition of this would lead to increased CNS ions. And so that would mean that there'd be a greater chance of these guys reacting and forming these products. So if we think about it, the stress being applied is the addition of these ions. So in an attempt to relieve that stress, in accordance with Le Chatelier's principle, this will favor the forward reaction. Okay, so what we'll see is the forward reaction being favored and concentration of Fe3 plus ions will decrease, so it will reduce. And part 2, explain why changing the pressure has no effect on this equilibrium. So the key thing here is we're seeing that the reactants and the products are in the aqueous phase. So the pressure doesn't have an effect on this liquid solution. So there's no gases here. So the liquids aren't compressible. So that's the answer to that one. And part C. Write the equilibrium constant expression for this reaction. Okay, so we'll have products above reactants. We've got the FeCNS 2 minus ion there, square brackets essential. Products over reactants, Fe3 plus square bracket. No coefficients to take into account. That's fine, check for that. Yeah, okay, square brackets, grand. That's our Kc expression there. Now, we get to setting up our ice table. So, a mixture of 1.0, so we're given the moles, just make some more room there. We're given the moles of iron 3 chloride and potassium thiocyanate in a 1 liter vessel. Okay, so let's set up our ice table. We've got write out the equation plus CNS minus brackets 2 minus. Okay, and we've got I, C, and E. Okay, so initially a mixture of, we've got 1.0 by 10 to the minus 3 moles there. And same over here, 1.0 by 10 to the minus 3. And over here, initially we've got 0 products. And then according to the equation, it was found that, okay, so this is the number of moles of iron thiocyanate at equilibrium. So there's an increase plus 1.1 by 10 to the, oops, what was it, minus 4. Okay, so so these will be reduced by that amount, minus 1.1 by 10 to the minus 4, minus 1.1 by 10 to the minus 4. Okay, so that leaves us at equilibrium. We've got 0.00089. Okay, so I'm taking this away from our initial concentration, and same here. And this is all in a 1 liter vessel, so I can have these in square brackets. If I want to write it in there, the square brackets, I can include them there. But even more importantly, I include them in the Kc expression. So I've got Kc equals my reactant, my products above my reactants each time. Okay, so there's my square brackets, essential, and then I've got 0.00089. I've got 2 of those, so I'm just going to square that. And if I do that sum, I get 138.87, and that's moles per liter. Okay, because that was, what have we got? Moles per liter over moles per liter by moles per liter. Cancel, cancel. So that's moles per liter minus 1. Or that can be written as, so if I could have these or moles per liter, so molarity, molarity. So I end up with 138.87 and molarity to the power of minus 1. Okay, was there another question? Yeah. So part D here, the red color faded when the test tube containing the equilibrium mixture was placed in an iced water bath. State whether the value of Kc for this reaction is bigger or smaller at lower temperatures. When the system was put under a cold stress, it went less red, it went to yellow. So when it favors this reaction, it went to yellow. When it was put in ice, therefore I know that this way is exothermic, and this way by process of elimination is endothermic. So so at cooler temperatures, the Kc value would reduce because there'd be less of this iron thiocyanate formed. So, and that goes up here. I'll go here. So this would decrease, this number would decrease, and these reactants in the forward reaction would increase. Okay, so this Kc value would decrease. And is the forward reaction exothermic or endothermic? Okay, we've done that, but let's justify our answer. Okay, so the forward reaction is endothermic. So we have to explain that with by elaborating on what we just went over. So when the system is cooled, the color goes yellow. So the system is trying to relieve the cooling stress. So it favors the exothermic reaction. So this, the reverse reaction is exothermic. So by process of deduction, the forward reaction is endothermic. So it's endothermic, and that's how we justify it. Okay.